Hello everyone! In this crash course we are going to learn how to use the Pymunk physics library. So if you want to learn more about Pymunk, just go to pymunk.org and here you can find the API reference, examples, showcases, tutorials, benchmarks and so on. So for short, Pymunk is an easy to use Pythonic 2D physics library and it can be used for games, demos and all sorts of physics simulations. And Pymunk is based on, or it is built on, the Chipmunk physics library. And I just opened this chipmunk-physics.net. And Chipmunk is written in C programming language. And Pymunk is written in Python. And the Pymunk is a wrapper around the Chipmunk physics library. Okay, let's go to PyCharm. And I'm just created a rough plan for this crash course. So here now we are in the intro section, and also in this section we are going to install and check the versions, so the Pymunk version and also the Chipmunk version. Then we are going to create a headless simulation or a basic simulation, so without any window, just in the command line. Then we are going to create a window using Pyglet. You can also use Pygame or all sorts of windowing applications or windowing libraries. Here we are also going to use a debug draw options to make our physical bodies visible in the window. Then we are going to take a look on the space, also the bodies, the shapes, how to create custom shapes, what is the moment of inertia, what is the elasticity and the friction, how to use images or sprites, how to use the collision handler, what is the arbiter object. We are going to take a look on point queries, raycasting, also joints and so on. So this is just a rough plan. Okay, so now let's take a look how to install Pymunk. So which is very easy, you just have to run pip install Pymunk in your Python environment. And because, as I said, I'm going to use Pyglet for windowing, I'm also installed Pyglet with the command pip install Pyglet. I already have a Pyglet crash course in my channel, so if you don't know what Pyglet is, you can watch that crash course. And to actually take a look what version we are going to use, so also the Pymunk version and also the Chipmunk version. So in order to see that, we can import Pymunk as PMK, or just import Pymunk. I'm just going to give it an alias of PMK, and here we can print out pmk.version, and this will print out the Pymunk version, and here pmk.chipmunk version, it will print out the Chipmunk version. So let's run it, right click and intro install, and as you can see I'm using now the latest version of Pymunk, which is 6.10.0, so the latest version when recording this video. And so this is the Pymunk version, and this is a wrapper around the Chipmunk C library. So the version of this Chipmunk library is 7.0.3. In this section we are going to take a look on how to create a basic simulation using Pymunk. So I called it basic headless simulation, but I also can call it basic windowless simulation, because the simulation what we are going to run will only be visible inside the terminal or the command line. So I have already created this 02 basic sim.py, and the first thing I'm just going to do here is of course import Pymunk as PMK. And I'm also going to create a so-called Pymunk space. And what is the space? I'm just going to I'm just going to create a separate section which will cover the Pymunk space. So each simulation needs a space. Now let's set the space gravity. So space.gravity equals 0 and -1000. This is a vector 2, so this is the x value, and we are setting the y value to -1000. The next thing we have to create is a so-called body, and I'm also going to create a separate section for the bodies. Just for now we are going to create this body with the following command. So body equals pmk.body, and we are going to give it a mass of 1 and a moment of inertia of 1666. Later we are going to take a look on these values, what these mean. And I'm also going to set the body's position. So this is also vector 2. Remember that Pymunk is a 2D physics library, so we can set values on the x and also on the y axis. So x is 50 and the y is 100. And the next thing we have to do is add this body to the space. So space.add the body. Okay, we are created the space, we are created the body. Now we have to continuously update this simulation. For this we will need a while loop, a while true loop, so an infinite loop. So while true, and next thing we have to do is actually step through the space. It will update the physics simulation. And you can do this by just adding this command space.step and give it a small value. I will give it 0.02, and 0.02 is roughly 50 frames per second. So if we divide 1 by 50, we will get 0.02. Okay, and the next thing, we are just going to print out the body's position to the terminal or the command line. So print body.position. So let's run this. Right click and run basic simulation. And now as you can see, it prints out a vector 2, and the x value doesn't change, it stays at 50, and the y value is decreasing, so the body is falling down. I'm just going to stop it, keyboard interrupt, okay. And what I'm going to do is just a little bit slow it down with the time.sleep. So I'm just going to import the standard module, Python module import time, and here after we print out the body position, I'm just going to give it a little bit of sleep. So time.sleep 1, so 1 second of sleep, so that we can see what's happening. And now as you can see, it started at 100 and it's slowly decreasing the y value. So 99, 98, 97, 96, 94, 91. And as it falls down, it accelerates. So that's why here is 99, 98, 97, 96, then it goes to 94, then 91, 88. So as you can see, the body, as it falls down, its falling speed is accelerating. Okay, it is pretty boring to see the simulation inside the terminal or the command line window. So that's why in this section I'm going to create the first window using Pyglet. You can use Pymunk with all sorts of windowing frameworks, libraries and modules. You can use it with Pygame, you can use it with matplotlib, you can use it with, I don't know, Python. I'm just going to show you something which I have created using Python at the end of this section. But for now, let's go to the sections, and here we are on section 03. Simulation in Pyglet window plus the debug draw options. So let me go for a second to pymunk.org, and here click on the API reference, and you will see modules which comes with Pymunk, and here are the submodules. Here you can find all the by default supported windowing frameworks or libraries. Here you can see Pygame, and also Pyglet is supported, and also matplotlib. So we are going to use Pyglet, and let me click here, and as you can see, here we have a draw options, and we can use this draw options object to visualize our bodies in the space. Okay, so let's go back to PyCharm and create a Pyglet window. And as I said, I already created a Pyglet crash course, so I'm just going to briefly go through it. So first we have to do is import Pyglet. I'm going to alias it as pglt, And the second thing what we have to do is just create a Pyglet window. I'm just going to call it window, so pglt.window.window. The window size will be 1280 by 720, and its caption will be Pymunk simulation, and resizable will be false, so we cannot resize a window. The next thing which is still needed to create an onDraw function. So onDraw, and I'm just going to clear the buffer of the window, so this clears the color buffer bit and also depth buffer bit in a Pyglet window. And the next thing I'm just going to do is create an update method. So, and this will update the physics simulation, and I'm also going to just for now give it a pass, and also create this if statement. So if __name equals __ main, although it is not needed technically, but I like to add this if statement. And I'm just going to call the pglt or pyglet.clock.schedule interval, and this will call repeatedly the update function every 60ths of a second. So this is about, let me see, 1/60. So every 0.016 seconds, so 16 milliseconds. And the last thing what we have to do is call the pyglet.up.run. So this will already create our window. So as you can see, we have a 1280 by 720 window. Here the caption says Pymunk simulation, and this window is not resizable. So now let's do the Pymunk side. And we also have to import the Pymunk. So import Pymunk as PMK. And the next thing I'm going to import is from pymunk.pyglet_util import the draw options. And you can find this if you go back. Here is the Pyglet util. As you can see, this is the Pyglet util draw options object. So let's go back. And I'm also going to create these options. So instantiate, so options equals draw options. And let's create also the Pymunk space here. So space equals pmk.space or pymunk.space. Also set the gravity as we did in the last section. So space.gravity equals 0 and -1000. Let's create also a body. So body equals Pymunk.body with the mass of 1 and the moment of inertia 1666. And also going to set the body's position, so it will appear on the top of the window. So body.position equals 640, so which is the center, horizontally on the center of the window. So remember that 1280 divided by 2 is 640, and I'm going to put it on top of the window, so it will fall down. And also let's create a shape so that we can see what's happening in the window. So you can create a box shape using the pymunk.poly.createBox, giving it first the body and also a size. So this will be a 50 by 50 box shape. And let's go back. I'm going to talk about the shapes a little bit later in section 0.6. And the next thing what we have to do is add the body and also this shape to the space. So space that add the body and the box shape. Also, we have to draw these options, so these draw options, and here in the onDraw method or function, we can call the space.debugDraw and giving it the options as its first argument. The last thing we have to do is in the update function, we just have to call the space.step, so step through the simulation, and giving it the delta time. And the delta time is this value, so 1/60, which is 16 milliseconds. And the very last thing what we have to do, so if I run this, we will see still nothing, because if you watch my Pyglet tutorial or a crash course, you will see that we have to give to this onDraw function at window event decorator. And now let's try it. And now as you can see we have a falling box. Let's try it again. Okay, so the box starts at this position, so in the center, horizontally in the center, and at 700, so on top of here. And as it falls down, it accelerates downwards. At the end of this section, I'm just going to quickly show you how you can use Pymunk with VX-Python. So by default, Pymunk doesn't have any debug draw options for a VX-Python application. So you have to use VX-Python's built-in shapes for drawing boxes, drawing circles, and all sorts of other shapes. So you can find VX-Python on vxpython.org, and you can install it from PyPy using pip install VX-Python. So let's go back to PyCharm, and here I already prepared a VX-Python and Pymunk simulation. And this code will be uploaded to my Patreon page, and if you are becoming a Patreon supporter, you can download this code. So I'm just here created usual stuff like a space, imported of course VX and also the Pymunk libraries. Here I created some Pymunk related stuff, also created a segment, so this is a circle and this will be a segment. Here I created a VX panel. I don't going to explain everything here, but let's run the application. And as you can see, we have this circle and we have this line which acts as a floor. And I created this VX-Python button. So if I click on this, it will start the simulation. And this is just a bouncing ball. Okay, so as you can see here, we are doing setting a timer, and we bind this event to the update function, and also here in the update function, where is the update here? In the update function we are stepping through the space. So space a step 0.016, and we are setting the self.x and self.y to circle.body.position x and negative circle body.position.y. And we are also calling the VX-Python's refresh function, which refreshes in every update call the window. Here in the onPaint, we are just drawing the draw ellipse. This draws the circle in self.x and self.y, and also drawing a line which acts as a floor. In this section, we are going to take a look on what is the space in Pymunk. So for that, I'm just going to the official website, and here click on the overview, and here you can find there are 4 basic classes you will use in Pymunk: the bodies, the shapes, the joints and the constraints, and also the space. So what is the space? Spaces are the basic simulation unit in Pymunk. You can add bodies, shapes and constraint to a space and then update the space as a whole. They control how all the rigid bodies, shapes and constraints interact together. The actual simulation is done by the space. Let's go back a little bit to PyCharm. In the previous section, we created a space, we set the gravity to 0 and -1000, here we created a body, here we created a shape, and we added the body and also the shape to the space. And here in the update function, we just step through the simulation, so space the step and with the dt. In 04 space.py, I have already imported the Pymunk and created a space object. And just let's quickly take a look how many properties and functions we have in a space object. So what we have already used is the gravity. You can set the gravity like this. So space.gravity equals and 2 numbers, which is one is the x and one is the y. So this is a vector 2. Let's go to the documentation and click on the API reference and also click on the Pymunk.space. And here you will find all the properties and all the functions or methods which are in the space object. Let's create a body and also a shape. So I'm just going to copy 3 lines. Body equals Pymunk.body, giving it a mass of 1 and a moment of inertia. Also set the body's position and also create a shape. And let's create one more body and one more shape. So body 2 position, and box 2, this will be the shape. So we can add also both body 1 and body 2 and box 1 and box 2 at once to the space with this command. So space.add body 1, box 1. So the body 1 and the shape 1, body 2 and the box 2. And I'm just going to quickly copy here a comment, so you can add multiple bodies and shapes to the space at once, like this. And for example, if you want to get all the added bodies from the space, you can just print out, for example, space.bodies, and this will return a list of bodies. So as you can see, we have 2 bodies, body 1 and body 2. So body 1 has a mass of 2, moment of inertia, its type is dynamic, and body 2 has a mass of 2, moment of inertia is 1.777, and the body type is dynamic. You can also print out the shapes added to the space. So print space.shapes, and here also this returns a list, and this list contains 2 shapes. So this poly object and this second poly object. So here we added, this is the first one, box 1, and this is the second one, so box 2. And here we added those also to the space. And let me go back to the documentation. So here under this section, Pymunk.space, you will find all the properties and methods. We have used this add. As you can see, it can take body, shape and constraint objects. We can add collision handler, we can add the default collision handler. We will take a look on this a little bit later. And all sorts of other properties and methods. We have used these bodies a second ago. We have also used this debug draw in the last section when we have drawn the space in a Pyglet window. So here is the gravity, which defaults to 0, 0. So you can also remove bodies and shapes and also constraints from the space, so they get removed from the physics simulation. And you can do all other stuff here. And one more information from the documentation. If I go back to the main site and click on the overview, just scroll down. Here you can read some interesting informations. So the mass, the weight and the units. So here I have set the space gravity to 0 and -1000. And what is this -1000? So sometimes users of Pymunk can be confused as to what unit everything is defined in. For example, is the mass of a body in grams or kilograms? So Pymunk is unitless and does not care which unit you use. So if you pass in seconds to a function expecting time, then your time unit is seconds. If you pass in pixels to a function that expects a distance, then your units of distance is pixels. So Pymunk is unitless. You will define what unit of measure you will use in your simulations. In this section, we are going to take a look on the bodies and the body types. So Pymunk has 3 body types: dynamic, kinematic and static. So let's go to the documentation and read a little bit. So API reference, and here open the Pymunk.body. Okay, just briefly check the documentation about the body types in Pymunk. So here is the dynamic, which is the default. So dynamic bodies are the default body types. This means that if you don't specify what body types you want to use, it will be set to dynamic. So dynamic bodies, they react to collisions, are affected by forces and gravity and have a finite amount of mass. So these are the type of bodies that you want the physics engine to simulate for you. Dynamic bodies interact with all types of bodies and can generate collision callbacks. Okay, let's check the kinematic body. So kinematic bodies are bodies that are controlled from your code instead of the inside physics engine. So kinematic bodies aren't affected by gravity and they have an infinite amount of mass, so they don't react to collisions or forces with other bodies. Okay, let's go to the static body. And static bodies are bodies that never or rarely move. So probably if you are creating a game, static bodies would be the walls, the ground, and the non-movable platforms. Okay, if you want to know more about the body types, just go to the documentation and read through all of these text. I'm going back to PyCharm and I already prepared something here. So 05_bodies. And here I have a Pyglet window and all the Pyglet related stuff. The only thing I have created on the Pymunk side is I have created a space and set the space gravity to 0 and -1000, and also created these draw options. So if I run, now I have just an empty window. So let's create the first body. Here I added this to do, add bodies and shapes. So the first body will be a dynamic body. So dynamic, and this is the default. So technically you can leave out the third argument because it is not necessary, it is the default. And in dynamic bodies you can set the mass of the body and also its moment of inertia. I'm going to talk about the moment of inertia in a later section. And the next body type is the kinematic body. So mass and moment are ignored when we are using a kinematic body. So here body 2 equals pmk.body, and the only thing I'm setting here is the body type. So pmk.body.kinematic. And the last body type is the static body. So static, mass and moment are also ignored in case of a static body. So you can set it like this: body 3 equals pymunk.body, body type equals pymunk body static. And the only thing I'm just going to add back to body 1, although it is a default, but just to be consistent with these two. Okay, now add these bodies to the space so that they are added to the simulation space that add body 1, body 2 and body 3. So we will still see nothing, although these bodies are in the space and they are part of the simulation. And of course, if you want to see them, you have to add a shape to them. But first of all, I'm just going to set their positions. So body 1 position will be set to 400 and 650, so XY. Body 2's position will be set to 500 and 650, and body 3 position will be set to 600 on X and 650 on Y. And the next thing what we are going to do is just add the shape to these bodies. Box 1 equals pmk poly create box, body 1, giving it the body 1 and its size. And also let's create the second box for body 2. So pmk poly create box for body 2, also its size. And for body 3 and also its size. And also add these shapes, these box shapes to the space. So body 1, body 2, body 3, and box 1, box 2, box 3. So let's run now the application. And the blue one, which fall down, was the dynamic body, so it is affected by the gravity. The green one is the kinematic body, which is not affected by the gravity. And the gray one is the static body, so this is also not affected by the gravity. So let me run it again. I'm just going to set the gravity a little bit lower, so let's say like -10 on the Y. And now the blue will fall a little bit slower. So as you can see, all these bodies are color coded, so dynamic, kinematic and static. Okay, in a context of a game, I would do the following. For dynamic bodies, which are affected by the gravity and other forces, I would set, for example, a ball, a player, or the enemies. Kinematic bodies, which are not affected by gravity and other forces but can be moved. I would also consider to create a player as a kinematic body, create platforms, doors, and movable objects as kinematic bodies. And for static bodies in a game which are not affected by gravity or other forces and cannot be moved, I would consider to add ground, building, and all sorts of immovable objects as static bodies. In this section, we are going to take a look on the shapes. And Pymunk comes by default with 3 shape types, so the circle, the box, and the segment. We have already used the box. For example, in the last section, we have these 3 squares, which are created with a poly.box or createBox function. And now we are also going to take a look on how to create a circle and also a segment or a line segment. So while the bodies define how a body should behave in a physical simulation based on its mass, based on its moment of inertia, based on its body type and friction and so on, a shape is just defines the body's shape, so how it looks like, where should it be colliding and so on. So let's take a look on these shapes. So I already prepared these 06 underscore shapes, and for now it is just an empty window. So let's create the first body, and I'm just going to call it segment body because this will use a segment shape. So this will be a static body, and I'm also going to set the body's position, so segment body dot position equals 0, 0. Now let's create 2 more bodies. One will be for the circle, so circle body, and this will be also static, and its position will be on 400 and 650. And let's create a last body. So this will be the box or square or rectangle, and let's set its position. So box body dot position 600 and 250. So these are just the bodies. So if you add these to the space, you will still see nothing. So space dot add, and let's add the segment body, also the circle, and also the box body. So I added all 3 bodies. And without the shape, body already added to the space. Okay, segment, okay, circle. Let me run it again. So as you can see, now we have some physical bodies in the simulation, but they don't have any shape. So that's why we need also add to them shapes, so that in one side they are visible in the simulation, on the other side they have a shape which defines its collision boundaries or physical boundaries. So let's do the shapes here after this comment. So the first shape I'm going to create is a segment shape. So segment shape equals Pymunk.segment, and you can read about this. So if you go to the API reference, here you will find the Pymunk.circle, here is the Pymunk.segment, and also here we will use also this Pymunk.poly, and this has a function which can create the boxes. So let's go back, and the first argument to the shape is the body, so segment body, and the next argument to the segment is its A point and its B point. So A starts at 0, 0, and its B point will be at 400 and 400, and its radius will be, or thickness will be 2 pixels. Now let's create also a shape for the circle body. So circle shape equals PMK or Pymunk.circle, giving it the circle body and circle's radius, which is 30. And the last shape I'm going to add is the box shape. So box shape equals pmk.poly.createBox. So we don't have something like pmk or Pymunk.segment or Pymunk.circle. We don't have pymunk.rectangle or pymunk.square. If we want to create a rectangle or a square, we have to do it like this: pymunk.poly.createBox, giving it the box body, so this one, and set its size. So this will be a width and a height, so 50 and 100. Let's add these shapes also to the simulation. So space.add the segment shape, the circle shape, and the box shape. And as you will see, Pymunk has a bug which we will solve soon. So let me run this. And as you can see, it gives this error, although it shows the shapes. So this is a circle, this is the segment, and this is the box. And at the background in the terminal, it just keeps giving this error. Okay, so let's take a look on how we can solve this bug inside Pymunk until it gets solved. So if you go to the Pymunk documentation, let's go to the main site, and here click on the issue tracker, and this will lead us to the Pymunk GitHub repository. And here, about 1 hour ago, as you can see, 1 hour ago, this guy called Akaosh IT created an issue related to our problem. So, need small update for new Pyglet version 2.1 to use shape.line function in Pymunk.Pyglet util. So we have this same problem as this guy. And as you can see, Pymunk still uses these in the draw options, in the Pyglet_util module, this width parameter. And also here in the draw segments, it uses this width equals 1 parameter. And this leads to an error, because now in Pyglet version 2.1, it is no more called width, but it is called thickness. So thickness equals 1 in this Pyglet.shape.line, and also in this draw segment function, it is also thickness equals 1, so not width equals 1. Maybe within 1 or 2 weeks it will be solved, and the guy who creates Pymunk, so I think Viblo, maybe he will solve it in the next release. But until it is solved, we can solve it by ourselves. So just go back to PyCharm and go to this module, so Pymunk.Pyglet util, open this module, so middle click with your mouse, and here you will find these draw options, and if you scroll down you will find this problem. So on line 127, so this Pyglet.shapes.line and position X, position Y, blah blah blah, but this width is giving us that error. And also in the draw segment, here also the same problem. So this should be thickness instead of width. So what I'm just going to do is going to duplicate this line and comment out this line, which gives us the error, and just replace it with this thickness equals 1. So go back and replace width with thickness. And also here in the def draw segment, just duplicate this line. I'm just going to comment out the line which gives us the error and replace this width with thickness, and save it and go back. And now let's try to run it, and now as you can see that error is gone. So we have 3 shapes: the circle, the line segment, and this rectangle. In the previous section, we took a look on what are the built-in shape types in Pyglet. So, and we have a circle, we have a line segment, and we have a box. And in this section, what we are going to take a look on is how to create custom shapes like a triangle and a pentagon. But first of all, before we create any shapes, just to let you know, Pymunk supports only convex shapes. So you can go to Google and search what is the difference between a convex and a concave. So convex versus concave. And here it says concave means hollowed out or rounded inward. And is easily remembered because these surfaces cave in, so this is the concave. The opposite is convex, meaning curved out or rounded outward. And let's go to the images tab, and here you will see some examples. For example, here is concave, so it caves in, and a convex. And here also it caves in, so concave, it has a cave, and this is a convex. And let's go also to Pymunk's documentation, and what we are going to use in this section is the Pymunk.poly object to create the vertices for our custom shapes. So I have already created two bodies. One is the triangle body, and its body type will be a kinematic body, and a pentagon body, and its type will be a static body, and also set their position. So the triangle's position will be 400 and 500, and the pentagon's position will be 600 and 500, so XY. And here are this to create the custom shapes. So the first shape what I'm going to create is a triangle shape. So I'm just going to call it triangle shape using the Pymunk.poly, so this module here. First argument or first parameter you have to give to the poly object is the body, so the triangle body, and then the vertices. So a triangle has 3 vertices. So this is the lower left, this is the lower right, and this is the middle vertex. So this triangle is 100 on X in size and also 100 on Y. And let's add this triangle to the space, and let's see it. So as you can see, we have now a triangle. Its size is 100 by 100, and it is a kinematic body. You can see it from its green color. Okay, now let's create one more for the pentagon, and this will be a little bit longer because this has 5 vertices. So pentagon shape equals Pymunk.poly, giving it as a first parameter the pentagon body we created here, and then the vertices. So this is the first vertex, second, third, fourth, and the 5th vertex. And also add this pentagon shape to the space, so now it is visible. So as you can see, it has this grayish color because it is a static body. And let's take a look on the vertices. So I'm just going to move it like this and run the application again. And here, so the triangle 0, 0 is this vertex here. The 100, 0 is the lower right, so this vertex, and 50 and 100 is this vertex. And the pentagon starts with this vertex, so in the lower left corner, then it goes to right, so 100, 0, then 150, 100, then 50 and 200, and the last vertex is here, negative 50 and 100. And there is one more thing I want to talk about in this section, which is the center of gravity. So let's go to the documentation and click on the overview and scroll down, and here you will find the center of gravity. So for example, if we have a rectangle and we start to define the first vertex with the, on the 0, 0 position, and then this is the second, third and the fourth vertex, the center of gravity will be on the lower left corner, which is not correct because the center of gravity should be in the middle of the shape. And also here, if you define a segment like this, 0, 0 and 6, 6, the center of gravity will be at point, the first point, so the 0, 0 point. So to actually transform the center of gravity, you can do 3 things. First of all, just create the vertices like this, so ranging from negative 3 and negative 3, so this is the first vertex, to negative 3 and 3, and 3, 3, negative 3, 3, so in this case the center of gravity will be in the middle. But you have also 2 more options. So this was the first option. You can set the body's center of gravity, for example equals 3, 3 as a tuple, or you can transform the shape using the Pymunk.transform module. I'm just going to do the first option, which is redefining the vertices. So let's go back to PyCharm and let's move the body's the triangle body to 0, 0 position, and you will see that where the center of gravity is. So as you can see, it now puts it in the lower left corner of the window. This means that the center of gravity is on the lower left corner of the triangle. So let's move it into the middle. For this, either you can do as in the documentation, so you can set the triangles or the triangle body's center of gravity, and this is the half width and the half height of the triangle, and let's try it. And now as you can see, we are only seeing a part of the triangle. The other part is hidden outside the window. I'm just going to comment out this line and redefine the triangle shape's vertices. So instead of starting from the 0, 0, so that from this position, I'm just going to comment out the line 22. I'm just going to create it like this. So negative 50, negative 50. So this is the lower left. 50, negative 50, lower right. And 0, 50. This is the upper vertex. Now let's run it. And as you can see, we have successfully moved the center of gravity in the middle of the triangle. And I'm just also going to add a little comment here. So this center of gravity is in the middle of the shape, and in this case center of gravity is at the lower left vertex of the shape. Okay, now let's do it also for the pentagon shape. I'm just going to comment out this one and add this one. So in this case we are starting now let me see. So now the center of gravity is in the middle of the pentagon shape, and I started with this vertex, so negative 100 and 0, then negative 50 and negative 100, then 50 and negative 100, 100 and 0, and 0 and 100. So here are the vertices. And if I move this pentagon shape, let's move the triangle back to, let's say, 500 and 400, and let's move the pentagon to 0, 0. You will see that we are only seeing the portion of the pentagon, and the other portion is outside the window. This means that the center of gravity is in the middle. In this section, we are going to take a look on how to calculate the moment of inertia for our physical bodies based on the shapes which are attached to the bodies. So first let's take a look on what is the moment of inertia. So just go to Google and type in moment of inertia, and let's open the Wikipedia page. So the moment of inertia, otherwise known as the mass moment of inertia, angular rotation mass or second moment of mass, or accurately rotational inertia of a rigid body, is defined relative to a rotational axis. It is the ratio between the torque applied and the resulting angular acceleration about that axis. It plays the same role in a rotational motion as mass does in a linear motion. A body's moment of inertia is about a particular axis depth both on the mass and its distribution relative to the axis, increasing with mass and distance from the axis. So maybe it is not the easiest understandable explanation. I would highly recommend to go to ChatGPT or Gemini or Claude and just ask those large language models. Maybe you will get a much easily understandable answer. Okay, let's take a look how we can calculate the moment of inertia in Pymunk. So go to the API reference and scroll down, and here you will find the functions for calculating the moment. So this is the moment for box, moment for the circle, moment for the poly, and moment for the segment. So let's go back to PyCharm, and I have already created this and added some to-dos. So to do a triangle, to do circle, and to do a pentagon. And I have already added this line segment, which is just a static ground. As you can see, its body type is static. And if I run the application, we have just a window and this line segment, and this will act as a ground for falling dynamic objects. Okay, so let's start with a triangle. And the first thing I'm just going to do is define the triangle vertices. I already showed you in the last section how to do this. So these are the triangle vertices, and this is a tuple of tuples. And now let's calculate the moment of inertia for this triangle. So triangle moment equals Pymunk.moment for poly, and we are using this function. And giving it the mass, and I created this mass variable which is equal to 1, and giving it the triangle vertices. And now let's print out what is the moment of inertia for this triangle. So print triangle moment. Let's run it. And as you can see, its moment of inertia is 1250. So okay, let's continue. And now let's create the triangle's body. So triangle body equals Pymunk the body, giving it the mass, which is 1, and the triangle moment. And also let's set its type to dynamic. And remember that the mass and the moment of inertia are ignored when you are using a kinematic or a static body. So only set the mass and the moment if you are using a dynamic body. So let's set also the triangle's position. So triangle body.position 400 400, and let's create also a shape for the triangle. So triangle shape equals Pymunk.poly, giving it the body and also the vertices. And now let's add this body and this shape to the space. So here space.add, and after the segments I'm going to add the triangle body and the triangle shape. And now let's run it. And we have this folding triangle, which when it touches the line, it's now interesting. Let's run it again. It just slides down. So this is how we can calculate moment of inertia for a triangle or a poly object. Now let's do this for the circle. So let's create a circle. I'm just going to calculate its moment. So circle moment equals Pymunk moment for circle, giving it the mass, and the inner radius will be set to 0 and the outer radius will be set to 30. Let's go to the documentation and click on the moment for circle. Here it is. Calculate the moment of inertia for a hollow circle. A solid circle has an inner radius of 0, so that's why I set here the inner radius to 0, because this is a solid circle. And also print out what has been calculated, so print circle moment, and let's run it. And as you can see, it has a moment of inertia 450. Okay, now let's add the body to the circle. Or let's create the body for the circle. So circle body equals Pymunk body, giving it the mass, here the circle moment, and the body type is also dynamic. Let's set its position. So circle position 600 and 650, and also let's create a shape for this circle. So circle shape equals Pymunk circle, giving it a circle body and the radius. And remember, this radius should be the same as for this moment for circle, so the outer radius. And now let's add the circle body and also the circle shape to the space. Okay, and now they are both added, so this is still running in the background. I'm just going to close this down and run it again. Now we have a circle, and as you can see, it also rolls down on the slope. And lastly, just create one more, which will be a pentagon. So for this, I'm just going to change a little bit the order, just to show you that it is possible to set first, for example, the polygon, and then set the moment from the polygon, and also lastly set the body. So let's set first the shape. So pentagon shape and Pymunk.poly, and for the body, I'm just going to set it to none, and later add a body to it. So the vertices will be the same as I created in the last section. So these are the 5 vertices for this pentagon. And also calculate the pentagon's moment of inertia. So pentagon moment equals Pymunk.moment for poly, and giving it the mass, which is set to 1. And you can also get the vertices like this. So pentagon shape that get vertices, and this returns a tuple of vector 2's. That's why Pymunk is underlying, because it awaits a tuple of float and float, but this get vertices returns a list of vector 2's, but it still works. It will not give any error. Okay, now do the printing. So let's check what is the pentagon's moment. And as you can see, its moment is 4250. Okay, now let's do also the body for the pentagon. So pentagon body equals Pymunk body, giving it the mass, giving it the calculated pentagon moment of inertia, and also set its body type to dynamic. Also, let's set its position, body's position. So pentagon body position will be at 800 and 700 xy. We have a shape, we have a body, but we cannot add a shape to the space without adding a body to this shape object. So that's why we are going to set the pentagon shape.body equal the pentagon body, and now we can add these to the space. And I'm just going to move this on the second line, and here add the pentagon body and the pentagon shape. And now let's run it. So as you can see, you can change the order of creating these objects. Here I created first the shape, then the moment, and then the body. And later on line 36, I just added to the shape's body property the pentagon body. Without this line, I'm just going to comment it out. It will give us an error. So assertion error, the shape's body is not set. In this section, we are going to take a look on the elasticity and the friction of Pymunk's shapes. So we are going to create a bouncing ball and also bouncing triangle. So let's go for a moment to the documentation, and let's open the API reference and click on the shapes. Here you will find all the properties and all the methods which are in a Pymunk shape. And here you will also find the elasticity and here elasticity and also the friction properties. This is the elasticity of the shape. A value of 0 gives no bounce, while a value of 1 will give a perfect bounce. However, due to inaccuracies in simulation, using 1 or greater is not recommended. Let's take a look on the friction. So friction coefficient, Pymunk uses the Coulomb friction model. A value of 0 is frictionless. A value over 1 is perfectly fine. And here are some real-world examples from Wikipedia. So if you want to have aluminium, copper, brass and so on, you can set the friction values to these. I have prepared a scene with 3 objects. So we have 2 dynamic objects, a circle and a triangle, and we have 1 static object, which is this segment or the ground. So let's first print out for the triangle the elasticity property and also the friction property. And remember, these are on the shape, not on the body. And as you can see, by default, both the elasticity and the friction are set to 0. So now let's try to change these values. Okay, at first I'm going to set the elasticity value on the circle object or the circle shape. So we can set it like this. So circle shape dot elasticity equals 0.9. And remember from the documentation that this value shouldn't be 1 or higher than 1. And let's see what happens now. And as you can see, we haven't set the elasticity on the triangle, but it still, for some reason, is still bounced. Okay, let's run it again. So for some reason, sometimes Pymunk behaves a little bit strange, so I haven't set any elasticity value on the triangle, but it still bounces. Okay, but the circle haven't bounced. If you take a look, it just bounces a little bit. So we should also set the, because this elasticity value is already pretty high, so also set the elasticity on the segment, on the line segment. So segment shape that elasticity equals 0.9, and now let's try it. And still the triangle bounces. Why? As you can see, I haven't set anything on the triangle, I mean no elasticity and no friction, so its default value should be 0 and 0 for the elasticity and also for the friction, but the triangle for some reason still bounces. So let's try again, and this is the correct behavior. So the not yet, because it bounced 2 or 3 times and it stopped bouncing. And I'm thinking that maybe when I don't record the video, it looks like everything works perfectly, but when I start to record the video, it just somehow, maybe my CPU is a little bit overloaded, I'm not sure. So as I said, everything works fine when I'm not recording the video, but when I start to record, it starts to behave a little bit strangely. So let's run it again. Okay, 2 bounces, 3 bounces, 4 bounces. Now okay, it looks like, I don't know what causing this strange behavior. So let's just shut down and let's try out. So here we set the segment shape elasticity and also the circle shape elasticity. So let's set the elasticity for the triangle shape, and let's see what happens. So triangle shape that elasticity equals 0.4. And now everything works as it should. So let's try to raise this to 0.9 also. Okay, let's try also the friction values. And the friction is interesting when we have a slope. So this is just a straight line, this ground. So we should have to raise it a little bit. So here when I create the Pymunk segment, I'm just going to, this is the A point and this is the B point, and I'm just going to raise the B point's Y value to, let's say, 100. Because the friction default value is set to 0, they are also the triangle and also the ball just slides down easily on the slope. So let's set the friction, for example, for the triangle to 0.8. And remember, if you go to the documentation, here are the friction coefficients, and here are some real world values for all sorts of materials. Okay, let's run it. Okay, I'm just also going to remove the elasticity from the triangle so that it won't bounce. And it slides down. But if I set its friction to 0, maybe I should also set the friction on the segment. Yep, let's set it to this value. And let's run it. I'm just going to set the elasticity also on the line segment to a little bit lower. Let's try it. Okay, now it doesn't bounce as much. But also the ball started to not bounce. So maybe I'm just going to raise it a little bit to 0.5. But the triangle shouldn't bounce because the triangle's elasticity is set to 0. So I'm just going to uncomment this and set it again to 0, but this is the default. And now it is okay. So the friction value, if I set the triangle's friction value to a higher value, for example to 1, it won't slide down. As you can see, it stays in the same position. For example, let's try it with 0.8. Again, interesting that the ball just fall down from the slope, but the triangle stays here. It doesn't slide down. If I set the slope of this line segment, for example, to 400, let me see what happens. And it slides a little bit, then it stops. Let's make its friction to 0.4, for example. And it slides. Okay, so the higher this friction value, it is, as you can see, it slowly but stops. So you should play with these values, the elasticity and also the friction, because that's the best way to actually learn how these are working together with the Pymunk shapes. Until now, we just use these debug draw options to visualize our Pymunk shapes, and in this section, so section number 10, we are going to take a look on how to load images and sprites using Pyglet, and also move these images and sprites based on the Pymunk's bodies. I have already prepared this file, which is the same as we did in the last section. So we have just this static slope, we have this ball and also, or the circle, and also this triangle. And here I added this to-do to load images as Pyglet sprites. And the two images I have prepared are in this images folder. One is this smile, and its size is 60 by 60. I have created these two images using Inkscape. So this is a 60 by 60 PNG, and the triangle.png, and this is 100 by 100. Okay, now let's start to load these two images using Pyglet. And the first thing what we have to do is actually, let's create a Pyglet image. And you can do this just by calling the pyglet.image.load function. And this is in the images folder /smile.png. So first we are going to load the smile. And then the next thing what we have to do is create a sprite from this image. So smile sprite equals pyglet.sprite.sprite with a capital S, and giving it a smile image, and also let's set its position to circle body.position.x, and the y will be circle body.position.y. And let's also draw this in the onDraw function. So let's just call the smile sprite.draw function or method. And let's run it. Okay, it stays in the same position. First, let's remove the gravity to 0. And let's see the first problem. As you can see, the image is offsetted compared to the shape. So we have to move the anchor point of the image to the left and also down. So half width to the left and half width or half height to down. So let's do this. Here, when we load the image, we can set the anchor point with the following command. So smile image.anchor x equals smile image.width divided by 2, and I'm using integer division here. And also let's do this for the height or the anchor y. So smile image.anchor y equals smile image.height divided by 2. And now let's run it. And now as you can see, the image completely overlaps the circle. And the circle size, the circle shape size is also 100 by 100. So here we set the, 60 by 60. So here we set the radius of the circle to 30, and the diameter of the circle is 2 times 30, so 60. And now let's add back the gravity, so negative 1000 here on line 10. And now the circle falls, but the image should also follow the circle. We should do this in the update function, which is being called every 60th of a second. Okay, so I'm just going to show you actually 3 ways to set the position of a sprite based on the Pymunk body's position. So the one way is just doing this. So set the smile sprite.x position to circle body position.x, and also the smile sprite.y position to circle body position.y. So let me see. Now as you can see, the image follows the circle shape. It should also rotate, so let's add a rotation to it. And we can add the rotation with the following. So smile sprite.rotation will be equal to the circle body.angle. So circle body.angle. And the problem here is that Pyglet uses rotation in degrees, but this returns the rotation in radians. So we should convert these radians to degrees. So if I run it, we will see no rotation at all, as you can see. So we should import from the standard Python math module the degrees function. And we can do this with from math import degrees. And let's use here the degrees function. Okay, so smile sprite.rotation equals the degrees of circle body.angle. And now let's see. And as you can see, now we started to rotate. But the one problem is it rotates in the opposite direction. So it rotates counterclockwise, not clockwise. It can be easily solved just by negating this circle body.angle. So let's give it a negative sign here. And now let's try it. And now it rotates properly. And one more thing, I just set the gravity to negative 100 instead of negative 1000. That's why those bodies are falling so slow. So let's try it again. And as you can see, the rotation is okay. So now let's do the same for this triangle. So the first thing what we are going to do is just load the triangle image using pyglet.image.load function. So triangle image will be equal to pyglet.image.load, and also remove this part, and it is in the images folder /triangle.png. Also create a sprite from this. So triangle sprite will be equal to pyglet.sprite.sprite with a capital S, giving it as a first argument the image, so triangle image, and let's set its x and y position to the triangle body.position x and the triangle body.position y. Also let's draw this triangle using the triangle sprite.draw method. Let me see. Of course, we should set back the gravity to 0, 0. And now as you can see, also the triangle has an offset compared to the Pymunk's shape. So we should also set its anchor point. So triangle image dot anchor x equals triangle image dot width integer division by 2, and triangle image anchor y equals triangle image dot height and also integer division by 2. And now let's see it. And as you can see now, the triangle image or sprite is overlapping the Pymunk triangle shape. Okay, now let's add back the gravity. And we should still also update the image sprite position. So let's do it in the in the update function. But before I will do it, let's just take a look how we can set the sprites X and Y position. So this is one way, and I'm just going to comment this out and just going to show you a second and a third way. So the second way to do this is with this. So second way is the smile sprite dot position, and this is a vector free, so X, Y and Z position, because Pyglet uses free axis. So here we should set circle body dot position dot X, comma circle body dot position dot Y, and for the Z value we will just set it to 0. And this also works, as you can see. So this is the second way, and I'm just going to show you the third way. So the third way is smile sprite.position, and here we are using the unpacking operator, Python's unpacking operator. So star circle body.position, so this will unpack the X and Y values to this sprite position, and also let's set the Z value to 0. And it also works. I'm just going to use this. Let's do the same for the triangle. So triangle sprite.position will be equal to the triangle body.position, and remember we have to unpack this, the XY values, and set the Z value to 0. And now it follows the shape, although it doesn't rotate with the shape, so let's add the rotation to it. Using the triangle sprite.rotation equals the degrees of negative triangle body.angle. And remember, this is in radians, so we have to convert this to degrees because Pyglet uses degrees. And now let's see it. And as you can see, now it rotates with the shape. If you will ever create a game or some simulation using Pymunk and Pyglet, you should also just remove the space the debug draw option, but I'm still going to use it because for this line segment we are still using the space debug draw options. So if I remove this line from the onDraw function, we will see our two shapes, but we don't see the ground anymore. So that's why we still need this space the debug draw. Probably the best way would be to actually add also sprites to the ground, but I won't going to do this. In this section we are going to take a look on the collision handler callback functions. Let's go to the documentation and let's open the API reference and go to the Pymunk.collision handler. And here you can read about the collision handler. So the collision handler has a set of 4 callback functions for different collision events that Pymunk recognizes. And these 4 functions are the begin function, the post-solve function, the pre-solve function, and the separate function. So we are going to define these 4 callback functions. Okay, let's go back to PyCharm, and I have already prepared this scene, and if I run it, it just has this bouncing smiley face. Now let's add the collision callbacks. Okay, the first thing what we have to do is, here I added these to-dos, so define the collision handler callbacks. So the first handler function will be the collision begin. So this one, begin, and this is a callback function. So collision begin takes 3 parameters. First is the arbiter object, the second is the space, and the third is the data, and this is a dictionary, and it returns a boolean. So let's return something, a boolean value of true. I'm also going to just copy and paste a comment here. The collision begin will be called when the 2 shapes just started touching for the first time this step. And I'm also going to just print out the begin. And now let's define the second collision function, and this will be the collision pre-solve. So this takes also the arbiter object, the space object, and also a data, which is a dictionary, and it should also return a true. or false, so it should return a boolean. And I'm also just going to add a documentation to it, and this is from the official Pymunk documentation. So this function gets called when two shapes are touching during this step, and I'm just going to print out the following. So print presolve, and let's do this for the remaining two functions. So the next function will be the collision post solve. It also takes the arbiter object, a space object, and the data, which is a dictionary, and this returns none. This is being called when two shapes are touching and their collision response has been processed, and I'm just going to print out post solve. And let's define the last handler function, and this will be the collision separate, and this also takes the arbiter object, the space object, and the data, and it also returns none. So just go back to the documentation, and as you can see here, the begin returns a boolean, the post solve returns a none, a presolve returns also a boolean, so here it is, and the separate also returns none. Okay, and the separate function is being called when two shapes have just stopped touching for the first time this step, and I'm just going to print out the separate. So now let's create an instance from the default collision handler, and we can do this just by calling the handler equals space.add default collision handler. And now let's add to this handler object the callback functions. So the first will be handler.begin will be equal to the collision begin function, so this function. And let's do this for the presolve. So handler.presolve equals the collision pre, so this function. And let's do this for the remaining two. Handler.postsolve equals the collision post, which is this function, and the handler.separate will be equal to the collision separate, so this function. And now let's run this application, and you will see here in the terminal what it prints. So when they are touching, the begin is called, then the presolve is called, the postsolve is called. When they are separated, so the circle and also the line are being separated, then the separate is called, and then it bounces back, so the begin is called again, then the presolve, the postsolve, and they are separated again because the ball is bouncing away from the line segment. Okay, now let's make a little bit more interesting, and here in this begin, collision begin callback function, I'm just going to play a sound when the ball is touching the line segment. And I have created this directory sounds, and I have added one sound, which is a sound.wave. And this wave file is just, I have generated this sound in Audacity. So it sounds like this. If you want to generate something like this in Audacity, here is the generate, and just use the reset drum and play with these settings here. Okay, and I have exported out this sound as a wave file, and I already added it in the sounds directory and sounds.wave. Okay, the first thing, we are going to load this sound using Pyglet. So sound equals pyglet.media.load, giving it the sounds directory / sound.wave file. And I'm going to set the streaming to false because I want to play back this sound multiple times. And here, when the collision begins, I'm just going to call the sound.play function. So I'm just going to comment out this begin and run the application. So as you can hear, when the two bodies are colliding with each other, then this sound is playing. So let's run it again. In this section, we are going to take a look on the arbiter object. So let's go to Pymunk's documentation, and I already opened the API reference, and here in the classes you will find the pymunk.arbiter. Let's open this. And the arbiter object encapsulates a pair of colliding shapes and all of the data about their collision. So they are created when a collision starts and persists until those shapes are no longer colliding. And also a warning here, because arbiters are handled by the space, you should never hold on to a reference to an arbiter, as you don't know when it will be destroyed. Okay, so here are all the functions and all the properties for the arbiter object. Let's go back to PyCharm, and I have prepared here this scene. We have these two line segments and this falling circle shape. And here are the collision handler callback functions, and as you can see, all of these callback function takes as its first argument the arbiter object. So let's print out what this arbiter contains. And in this section I'm just going to work in this collision begin callback function. So all these just returns a true and this just passes. Okay, so let's run it and let's see what it will print. So as you can see, we have this pymunk.arbiter.arbiter object. So this arbiter object has, for example, several properties. One is the touching shapes. So we can print out arbiter.shapes. Let me see. And as you can see here, we have a circle, so the smiley face, and also the segment shape when they are colliding. What I'm going to do in this section is when the circle touches the second line segment, it will be removed from the simulation. So let's do this. So the first thing I'm going to do is set this second segment shape to a sensor. So we can do this with this one command. So segment shape 2.sensor equals true. So now this shape will become a sensor. So if I run it, the circle will just fall through because this is no more a part of the physical simulation. And after that, in this collision begin callback function, I'm just going to ask the following. So we already printed out the arbiter.shapes, and I'm just going to ask if the arbiter.shapes at index 1 is a sensor, so that sensor. So remember that when we print this arbiter.shapes, it returns a tuple, and the first index is the circle shape and the second index is the segment shape. So that's why we asking here if the arbiter.shapes at index 1 is a sensor. We are just going to remove from the space, so space.remove the circle body and the circle shape. So let's try it. And as you can see, although Pyglet still draws the sprite, but the body and the shapes are removed. Now let's remove also the sprite. We just have to go to the onDraw method, and here only draw the sprite when the circle body and the circle shape are in the space. So we can just add here an if condition. So if circle body in space.bodies, then draw the smile. And I'm just going to print out two things, the space.bodies and the space.shapes. And as you can see, it prints out the three bodies, so static body, second static body, so the second line segment, and the dynamic body, which is a circle. And here the print shapes also prints out a segment shape, and a Pymunk circle shape. So here, if a circle body is still in the space.bodies, it has not been removed yet, then we are going to draw the sprite. And as you can see now, the body, the shape, and also the sprite are removed. And we can do one more thing here, in case if we want to be a little bit more specific, we can also ask, so if circle body in space.bodies and circle shape in space.shapes. So this is a little bit more specific, because here, when the circle touches the second shape, we are removing the circle body and also the circle shape. And it works as expected. In this section, we are going to take a look on the point query. So let's go first to the documentation. And I have already opened the API reference and click on the Pymunk space. And Pymunk space has the method for querying points. So let's just scroll down. And for example, here you will find the bb_query, which is a bounding box query. A little bit lower, you will also find the point query and the point query nearest. We are going to use this point query nearest. And it says that query space at point the nearest shape within the given distance range. Let's take a look on it in PyCharm. And I have already prepared this scene. It just draws 3 shapes with 3 bodies. So a dynamic body, a kinematic body, which is this box, and this line segment, which is a static body. And what I'm going to do is make these objects clickable. So whenever I click with my mouse pointer on these bodies, these shapes will detect the mouse click. So for the click event, we are going to use the Pyglet's onMousePress function. And if you want to know more, I have a Pyglet crash course created about 1.5 years ago. Okay, so the first will be the onMousePress, and this takes an X and Y position of the mouse inside the window, and these are both integers, the button and also a modifier, so these are both integers, and the button is the left, middle or the right mouse button, and the modifiers are the, for example, control click or shift click or something like that, and this returns none. And here in this function I'm just going to call the space.pointQueryNearest. So I'm just going to create a local variable called pointQ or pointQuery, and this will be the space.pointQueryNearest, and giving it as a first point the XY position of the mouse. The distance will be 0, and third parameter should be this Pymunk.shapeFilter. Okay, and now let's print out what this contains, this point query. Okay, let's run it. Click here and nothing happens. Let me see. Of course, we have to add the event decorator, so the window.event decorator. Without this, Pyglet will not detect the mouse click. So let's run it again. And now let's try to click on this circle. And as you can see, we get back these objects, so point query info, and you can find this object in the documentation also. If you go back, here is the point query info. Now what we are going to do is first, let's go back a little bit to the application, and if I click on a black part, as you can see, it just returns none. And whenever I click on a shape, it returns that shape. With this, we can ask if shape has been clicked, like this. If point query, so if this is not none, I'm just going to print out what we have clicked. So print the point query.shape and also print out the point query.shape.body. And let me try this. And now if I click, let's say, on this circle, it prints that it is a Pymunk shapes circle object and its body type. So body with its mass, with its moment and its type, so dynamic. Let's try with this green, which is a kinematic. So Pymunk shapes poly and its type is body.kinematic. And lastly, let's try with this static line segment. And as you can see, Pymunk that shapes a segment and its body type is static. And this function pointQueryNearest with the onMousePress can be very useful when you are creating, for example, GUI elements like clickable buttons or so on. Also in a game, if you want to detect a click on a player or on an enemy, you can use this functionality. And I'm also going to show you how to use mouse drag functionality. So for this, we are going to define one more function. And this will be the on mouse drag, and this you can find in the Pyglet's documentation. It also takes an X and a Y position of the mouse pointer, so these are integers, a dx and a dy, which is a delta x and a delta y, and also a button, which is an integer, and the modifiers, which is also an integer, and this returns also none. So let's do the same here. So do a point query, space.point query, nearest, also giving it the xy position of the mouse, the distance will be 0, and also giving it this Pymunk.shape filter. Also have to add this Windows event decorator, so without this Pyglet won't detect this on mouse drag function. And here also going to ask if we are clicking on a shape, so if point query, then we are going to move shape's body's position to the xy of the mouse position. Point query that shape that body that position equals xy, and I'm just going to comment out this on mouse press and just run this on mouse drag. Let me try this. So if I click on this circle, now I can drag, and I'm holding down the left mouse button. So let's do this also with this kinematic body, and as you can see it works. There is a little small problem. So if I, let's say, click here in the lower left part of the shape, it will just jump to the mouse position as soon as I start to drag. This can be easily solved, but I'm not going to do this in this video. So the dynamic and also the kinematic body can be moved like this, but the static body doesn't work. So if I click and start to drag, nothing happens. So let's go back to the documentation, and here let's click on the Pymunk body, and here you will read that static bodies are bodies that never or rarely move, although you can move a static body. Here it says static bodies can be moved, but there is a performance penalty as the collision information is recalculated. So technically we don't have to move the static body. In this section we are going to take a look on the segment query. So what we are going to do is a simple raycasting. So let's go to the documentation for a moment, and here you will find a segment query info class, and let's see what it does. So segment queries return more information than just a simple yes or no. They are also return where a shape was hit and its surface normal at the hit point. This object holds that information. And one more thing, segment queries are like raycasting, but because not all spatial indexes allow processing infinitely long ray queries, it is limited to segments. Okay, let's go back to PyCharm, and here I already prepared this scene. It just has this dynamic, this kinematic, and this static body. And I also set the gravity to 0, 0, so the dynamic body doesn't fall down. And one more thing, let's go back to the documentation. The segment queries you can do through the space. So let's open up the Pymunk.space. And the same as with the point queries, you have a method for segment queries here in the space class. So just scroll down, and here you will find the segment query and also the segment query first. We are going to use the segment query first, and query space along the line segment from start to end with the given radius. The filter is applied to the query and follows the same rules as the collision detection. So, okay, let's do it. Okay, what I want to do is, if I click, it will draw a line, and if this line interacts with a body or a shape, it will just draw it red. So let's do it. I'm just going to add a mouse press event. So on mouse press, and it takes the XY button and the modifiers, and it returns none. So here we are going to do the segment query. So I'm just going to create a local variable called segment_q, and using the space.segmentQueryFirst function, and this has a starting point and an ending point, and the starting point will be 0, 0, so the lower left corner of the window, and the ending point will be the mouse click position, so XY, and its radius will be 1, and it also has this Pymunk.shape filter. Let's just print out what this contains. So print segment underscore q, and let's run it. And if I click on a black area, it just intersected this kinematic body. And if I click here, for example, so try to imagine a line from the lower left corner of the window to the mouse click position. And if this line doesn't intersect any shape, then it just returns none. So let's draw also this line. For that, I'm just going to remove this print and add an if condition. So if the segment query returns something, so it is not none, I'm just going to also print for a second what shape and what body was intersected. So print segment q.shape and segment q.shape.body. So let's try this. And here, of course, nothing prints, but if this line intersects, for example, this box shape, now it returns Pymunk.polyObject and body kinematic. Let's try it also with this dynamic shape. And as you can see, this line intersected the circle and its body. Okay, now just save the intersection point to a variable in this if condition, and I'm just going to comment out this print. So contact point will be a segment query.point, and this is a vector too. And here I'm just going to draw using Pyglet's line object, the line. Okay, we also have to import this module from Pyglet. So let's scroll up and just import like this. From Pyglet import shapes, and as I said, I have a Pyglet crash course and I already covered this module in that crash course. So here we are creating a line object and the shapes.line, and the starting position of the line will be at x, y, 0, 0, and the ending point will be at contact point.x and contact point.y. So that's why we saved here this segment query.point into this variable. And the line thickness will be 2 and its color will be 25500, so it will be red. And what I'm also going to do is just create a list of lines. So lines equals an empty list, and here after there is an intersection, I'm just going to add this line to the lines list. And let's draw this list of lines. So here in the onDraw, I'm just going to add for line in lines, line.draw. And now let's see. Okay, if there is no intersection, there is no line to draw. But if there is an intersection, let's see now, it will draw a red line. Also try it with this. This. So as you can see, this is a kind of a raycasting. Okay, now let's make it a little bit more interesting. So these lines will be drawn for 1 second, and it will also draw a line when there is no intersection, but in that case it will draw it as a white line. Okay, here in the on mouse press, so if there is no intersection, then we are going to add an else clause. So else, we are also going to create a line. So line equals shapes.line starting from 0, 0 and ending at xy. So the mouse click xy, and its thickness will be also 2. And by default the color is set to white. And I'm also going to append this line object to the lines list. So let's try it. And let's say I will click here. So as you can see now it draws white lines when there is no intersection, and when there is an intersection it draws it as a red line. And just one more thing I'm just going to add to this on mouse press is schedule once timer, which will just remove after 1 second the lines from this lines list. So here after this else, but outside the if condition, I'm just going to add this pyglet.clock.schedule once, and I'm just going to create this function, so remove line and a delay of 1 second. So here, after this lines list, I'm just going to add this remove line function. It takes a delta time, so which is a float, and it returns none. And in the body of this function, we are just going to loop through the lines list, so for line in lines, and remove the given line. So lines that remove the line. Okay, now let's try it. So if I click here, after 1 second, it will disappear, and also the red lines. This is the final section of this crash course. There are still some stuff I haven't covered in this course, but I'm planning to do shorter, maybe 10 to 15 or 20 minutes long videos covering Pymunk and also Pyglet. For example, in Pymunk I still want to create videos about the joints, also the shape filters, and for example also how to use Pymunk with Pygame and some other stuff. The codes written in this course will be uploaded to my Patreon page, so where you can download them if you become a Patreon supporter, and the link will be in the video description. At the end, if you found this video useful, just please give it a like. It doesn't cost you anything. And if you have a minute or so, please leave a short comment, because it helps the YouTube algorithm. Okay, so thanks for watching, and of course, have a nice day.